Hello everyone, very welcome to today's data learning talk. So today we're very happy to have Said Ouala from IMT Atlantique, and he will talk about data-driven and learning-based approach for the modeling, forecasting, and reconstruction of geophysical dynamics. So Said, I will leave the audience with you.
Thank you, Sibo, for this kind introduction. I would also like to thank you, Sibo and Resela, for inviting me to share my work with you today. I'm Said Ouala. I'm postdoc at IMT Atlantique in Brest, France. And I'm going to talk to you today about I've been doing for like since 3 years ago with my supervisors and collaborators regarding data-driven layer-based approaches for the modeling, forecasting, and construction of geophysical dynamics with a main focus on ocean surface dynamics. So a quick overview of what we will be going through, at least for this presentation today. I will start with some introduction and problem formulation. Then I will talk to you about three of the contributions that we propose regarding the modeling and forecasting and reconstruction of geophysical dynamics, and we'll end up with a conclusion and some perspectives. Okay. So in physical and satellite oceanography, and especially in ocean circulation-based applications, two main ingredients are typically exploited, which are the models and the observations. Now, roughly speaking, the models are necessary for forecast-based applications, and the observations are needed in order to state about the actual state of the ocean, and also in order to calibrate and validate the models. Now, combining these two ingredients in data assimilation frameworks provides, for instance, some solutions regarding, and from a modeling point of view, the initialization of the model, and from observations and data point of view, the reconstruction and interpolation of gap-free maps. Now, unfortunately, several issues still persist in both these two worlds, and especially in the link between the two. And specifically, and from a modeling perspective, a central question, which is somehow a very fundamental one, is how to make the models closer to the true state of the ocean. This includes the treatment of various sources of errors, such as numerical discretization error, model bias corrections, the choice of some parameterizations that usually involve some domain expertise. There is actually another question of how to make the models closer for a long time to, how to increase the predictability of the models. And these predictability issues for sure link to all of the previous questions regarding the modeling errors, but the predictability of problem of ocean circulation models is actually linked to the quality of the initial conditions that are given to the models to start with. So it makes it directly linked to the quality of the observations. Now, there is another question regarding how to derive reduced order models that can faithfully catch the variability of a subset of ocean processes, and for applications ranging from forecast to data assimilation. Now, from an observation point of view, there is this central question of how to make sense of all of these big amounts of data that come in every day from either satellite remote sensing sources or from in-situ networks. Another question is how to build on the current state of ocean models and the current availability of the observations to design new sensing missions that can improve our understanding of the ocean circulation. Now, in another word, artificial intelligence has already revolutionized several signal processing fields, such as image recognition, super resolution, and image translation. Now, the success of AI techniques is mainly due, at least from a practical point of view, to the increasing availability of computational power, as well as the increasing availability of the observations. Now, this success naturally motivated investigations within various other scientific fields, including satellite and physical oceanography, where the increasing availability of model simulations and the increasing availability of observations of the ocean naturally sets up the field with proof of concept showing the potential of AI in improving ocean models and in better exploiting ocean observations and eventually in closing the gap between the models and the observations. Within both the AI and physical and satellite oceanography communities, there is a huge emphasis in defining and solving problems efficiently using new adapted artificial intelligence tools. And this actually gave birth to a wide range of new methodological questions written in the language of physics-informed AI, starting from actual ocean situation models and how to make them better, up to the learning of new data-driven models that can faithfully catch the variability of some of the ocean observations. Now, there is also another class of questions regarding how to use artificial intelligence in order to make sense of all of the ocean observations. Now, in this work, we mainly focus in these last 2 points, and we aim at deriving data-driven representations for ocean surface variables that can be useful for forecast simulation data simulation applications. We are most of the time guided by physical and mathematical considerations regarding the underlying dynamics, because we know that at least from our own experience and from the current trend in state-of-the-art literature, that physics-informed AI is the way to go, at least in order to tackle such a complex system, which is the ocean. Okay. So the general framework used throughout all this work is classical state-space model formulation, where we assume that there is some hidden state Z that evolves in time according to some unknown differential equation, and we are provided with some observations X that are linked somehow to this hidden state Z. And within this formalism, we are asking ourselves how to use AI in order to extract models from observations that can be useful for forecast simulation and reconstruction of geophysical dynamics. Now, obviously, this question is linked to several considerations regarding the provided observations, and especially regarding the noise, the sampling operator, and the observation model age. Now, when provided with observations that are the full state Z, several kind of state-of-the-art techniques can be used in order to kind of reverse engineer the governing equation from from sequence of observations. When also provided with noisy observations of the state vector Z, and it will depend on the type of the noise, but most of the time, data-driven techniques can be defined jointly or after some kind of denoising of the observation. Now, when provided with noisy and irregularly sampled observations, there is a current trend in state-of-the-art techniques in investigating learning-based approaches in data assimilation frameworks. Now, interestingly, such a methodology actually links to classical kind of deep learning generative modeling in the context of the variational autoencoders. Another question is when we are provided with observations that are linked only partially to our high dimensional time evolving system Z, and in such situations, most of the time, all of the previously mentioned state-of-the-art techniques do not apply, and we need to define some kind of higher dimensional space. And in most of the state-of-the-art literature, people are using what we call delay embedding coordinates with regression, where recurrent neural networks can be seen as temporal propagators of these embeddings. Now, the applications of these state-of-the-art techniques need to be considered with care in order to account for the proper specifications of ocean surface observations. Ocean surface observations are temporally sparse, either when considering actual satellite remote sensing observations, for which and for some variables, the temporal resolution will depend on the return times of the satellite, which leads to huge spatiotemporal gaps in sampling of the observations, or either when considering actual model simulations where the temporal resolution of model simulation products is usually days, which misses faster variability that is necessary from a modeling point of view. Another issue is that ocean surface observations are just a tiny subset of a much more higher dimensional and complex time evolving system, which is the state of the ocean. And in this context, how to make sense of the ocean observations alone in order to derive a model that faithfully catch their variability. Another issue is that the ocean surface observations are irregularly sampled in space and time, which makes necessary the development of new kind of interpolation techniques, or more generally data assimilation techniques that can help enfolding higher resolution reconstruction out of the irregularly sampled observations. So in this presentation, we formulated our contributions as the solutions of three main questions. The first one is regarding the sparse temporal sampling. The question number 2 is how to deal with partially observed system, or how to model partially observed systems. And question 3 is how to use ideas of question 1 and question 2 in formulating data-driven data assimilation frameworks. Okay, so in the first part, sorry, of this of the technical part of this talk, I will mainly kind of introduce extremely quickly how to do learning of dynamical systems, and I will talk a little bit about numerical integration from an identification perspective. So in order to give kind of a quick overview of how to use learning-based approaches and deep learning in the context of the identification of dynamical systems, let's start from a dynamical systems point of view, where we are provided with some differential equation, and we want to solve this differential equation in order to predict the future. Now, most of the time, analytical solutions do not exist, unfortunately, or fortunately, yeah, that's why we have jobs, right? And we are kind of obliged to use numerical integration in order to simulate the equations. Now, from a learning point of view, we do not know these equations, but we are provided with some observations, and we want to find a model that catches the temporal variability of these observations. Now, from a deep learning point of view, classical deep learning architectures written as deep composition of elementary functions can be used for this task. They are, however, limited. They are extremely hard to diagnose when things go wrong, which also makes them hard to constrain. So throughout all this work, we will use what we call a neural Ode formulation, where the data-driven model is simply the time integration of an approximate differential equation. And such formulation actually have the benefits of using all of the state-of-the-art literature on dynamical systems, differential equations, and numerical integrations in order to kind of diagnose and constrain the optimization problems. Now, this formulation actually arises lots of questions regarding, for example, the space in which this model should be defined, the parameterization of the model, and the integration scheme. And in this in the first part of this talk, I will mainly focus on the integration techniques, or which integration techniques to use in the context of identification. So in order to give to kind of write the previous cartoon in a more formal way, let's assume that we are provided with a collection of measurements of a time varying dynamical system. And we want to find some dynamical model that catches temporal variability of these measurements. Now, assuming that we know some parameterization, let's say that F is, for example, a neural network, and we want to compute the weights and biases of this neural network. So how do we do that? And there's actually two kind of first order solutions, which are solution number 1, continuous time setting, in which the parameters of the models are computed by minimizing the mismatch between the output of the model and some estimate of the time derivatives. And the issue within this formulation is that we need to estimate time derivatives, right? And this estimation can be extremely challenging, especially when provided with noisy measurements. And in the context of ocean surface observations, where the temporal samplings are sparse, the correct estimation of the derivatives becomes impossible. Another technique is to do a discrete time setting in which we discretize this approximate differential equation, or this approximate dynamical model, and we optimize the parameters of the model with respect to a forecasting cost of the observations, or with respect to an integration cost of the dynamical system. So in this setting, we do not have the issue of estimating derivatives, but we have the question of which integration scheme to use. And actually, this question of choosing integration scheme is not as straightforward as it may sound, and especially it's not simple to it's not simple to choose an integration scheme for integration applications for which the ODE is known. For instance, we need to make sure that the integration scheme is stable with respect to the ODEs, with respect to the timescales of the ODE, and with respect to the integration time step. And what we do in practice actually is that we call ODE integrate from NumPy and SciPy packages. And what happens in ODE integrate in these packages is that we give our differential equation and we give a temporal sampling. We do not even give the integration time step because the integration time step is computed automatically. We do not know actually even the integration technique that is used by the solver, because the integration routine actually switches between different solver in order to kind of achieve a trade-off between the precision and the computational complexity of the solution. And actually some solvers do have automatic switching between stiff and non-stiff solver. All this to tell you that in practice, time integration solvers are black boxes. And from identification point of view, we do not really know which integration technique to use. So there is this solution of Chen et al. 2018 in his famous neural ODE paper, where he proposed to use adaptive step size solver in identification applications. Now, this is an extremely clever actually solution because we do not have to care about the timescales of the ODE that we do not know. We do not have to care about the integration time step using identification scenario because everything is done automatically. Now, the issue within using adaptive step size solver in identification applications is that we need to compute the backward pass of the adaptive step size solver. And if you use classical kind of residual neural networks techniques in order to compute this backward pass, we will need to store every single evaluation of the approximate ODE, which can lead to memory blowups. And if we use, as proposed by Chen et al. 2018, an adjoint sensitivity method in order to compute the backward as the solution of an augmented ODE that is integrated in backward time, integrating in backward time ODEs is an extremely ill-posed problem, and it can lead to instability issues. So from here, what we proposed is to define integration schemes based on application-oriented cost. And the idea here is illustrated throughout this scheme for an identification problem, where we assume that we are provided with some data and we want to find a model that catches the temporal variability of this data. So we assume a neural network F theta, a neural network differential equation. And we integrate this neural network using a Q stages Runge-Kutta scheme. We then may optimize the parameters of both the neural network that mimics a differential equation, as well as the parameters of the Runge-Kutta scheme to minimize the forecast of the observations. I will not talk too much about this contribution to have the time to talk about something else, but basically what happens by using such methodology is I'll move here. Yeah, what happens is that by learning integration schemes jointly with dynamical systems, what happens is that the integration schemes adapt to the dynamics of the observations, in the sense that if the observations are mainly dominated by an advection process, the integration scheme will be more stable towards the imaginary axis of the stability region. Also, if stability constraints are not necessary because the observations are generated from some kind of slow dynamical system, what happens is that instead of increasing the stability region, the integration scheme actually increases the order of integration, which makes the solutions more precise. Okay. Okay, So the second question we want to answer in this work is how to model partially observed systems. And it can be resumed as the following. So assuming that we are provided with some ocean-related observations X that follow this state space model, how to derive something that like this temporal propagator that models the observations. Now, the issue is that in order to write such a differential equation, you need to make sure that H, so the observation model H, is an embedding of the higher dimensional state Z, which means that this observation model needs to be one-to-one. So the projection from the high dimensional space to the space of the observations is done without any loss of information. And this observation model also needs to be an immersion. So the projection from the high dimensional space to the space of the observations is actually preserves the tangent directions. And why do we want to care about this this observation model being an embedding? Is simply to make sure that the deterministic behavior of the hidden state Z is still deterministic, which means predictable in space of the observations. Now, in order kind of to give some intuition about why to have such considerations in the context of modeling ocean surface variables, let's consider observations of the sea surface temperature X. Now, we know from physical oceanography that the evolution of the ocean's temperature is governed by a set of primitive equations. And so in this kind of high dimensional dynamical system, the variability, our observations are just a tiny two-dimensional layer of a much more complex higher dimensional system that involves other processes and that evolves in 3 dimensions. Now, if we assume that somehow the variability of the ocean surface temperature can be decoupled from the other ocean processes and the ocean depth, there is another source of missing information, which is the unresolved scales. The ocean variability is a multi-scale spatiotemporal system, and the provided observations, for example, observations of ocean surface temperature, have limited spatiotemporal resolution. It's for the sea surface temperature, it's 100 kilometers times days. So this misses on all of the faster and smaller unresolved variability that actually influences the large-scale variability, and this variability is actually primordial from an identification point of view. So from here, we need to find a space that forms an embedding of the hidden state Z. And in order to do that, we either do some synergy study and we try to include other observations that when stacked with our initial observations of the sea surface temperature will make sense of the observations, and we can do prediction on this new space. But this, in the context of ocean surface observations, will pretty much send us back to primitive equations which we want to avoid because they're extremely costly. Another solution is to use Taken's delay theory, in which when we are provided with some observations that are coming from a higher dimensional space, we just form a higher dimensional embedding by concatenating large versions of the observations. Now, the issue within Taken's delay embedding in modeling something as high dimensional as the ocean surface temperature is that we do not know how to parameterize this embedding. It's extremely complex to get a correct embedding for something that is not that is more than scalar, and even if we manage to get a reconstruction of the phase space, so even if we manage to get the correct embedding, the relationship between this embedding and any form of temporal propagator that propagates in time this embedding simply do not exist. And at the end of the day, that's what we want to do, right? We want to do forecast of the observation. So we need to find something else. So what we propose from here is to search for the most appropriate kind of higher dimensional system that explains the most the variability of the observations with respect to a given dynamical system. And how do we do that? Is simply by assuming that we are provided with some observations that are coming from a higher dimensional space. We send up these observations into another higher dimensional space U. So it's formed by some transformation of the observations. So M of X here can be used, for instance, in the context of reduced order modeling. And it is concatenated, to other what we called here latent variables. And we assume that this higher dimensional space is governed by a differential equation. We then minimize the forecast of the observations with respect to both the parameters of the neural ODE model and with respect to the initial conditions of the latent states. So the first term here in the loss function is simply the minimization of the forecast of the observations. And the second term here can be seen as a regularization because it makes sure that the inferred latent states here are not kind of computed independently for each time step. So after optimization is finished, what we can do is that what we end up with, a geometric reconstruction of the phase space. So pretty much what taken delay embedding does, but we also end up with a dynamical system, F theta, so neural ODE model that can be used to forecast the observations. As a first case study, we tried this framework on classical Lorentz 63 dynamical system, in which we assume that we observe the first state of Lorentz and we never observe the other two states. And we built our augmented state U with dimensions ranging from 3 to 6. So as a first experiment, what we did is that we want to visualize the spawned manifold of U as we minimize the forecast of the observations. So in the training set. And what actually happens is that so epoch 0 here is before starting the optimization. So we start up with pretty much noise on the initial conditions of the latent states. As we minimize the forecast of the observations and as we optimize the dynamical system, we end up with pretty much a reconstruction of the actual Lorentz 63 attractor. We also end up with a dynamical system that can be used to forecast the observations. And when compared to kind of classical delay embedding state-of-the-art prediction techniques that use recurrent neural networks, we are the only one that are able to kind of recover the chaotic variability of the Lorentz 63 model. The LSTM model, on the other hand, gets stuck on some kind of periodic loop. This is not good. Okay. We then started having some investigations regarding the attracting region of the spawned attractor. And what we figured out is that actually this attracting region was quite small, which is very, very bad, because if we pick up an initial condition that is a little bit farther from the observations, we do not go to the reconstructed Lorentz attractor, but we go to another limit set, which is most of the time unstable. We also figured out that we can make our models actually diverge to infinity from a perfect initial condition simply by running them for long periods of time. And this is extremely bad, both from a forecast and especially data assimilation point of view, where if our analysis sends us somewhere here, we can directly make our model diverge, which also makes the data assimilation model diverge. So from here, we started kind of investigating how to make our models bounded. And there were mainly kind of two roads to take within achieving the boundedness of the model. The first category of techniques or learn-based approaches and Lyapunov stability mainly comes from learning and dynamical system community, where you try to regularize your learning problem with satisfying Lyapunov stability condition. Now, the issue is that we don't actually want our models to be stable. We want them to be bounded but unstable so they can reflect the chaotic variability of the observations. And this is simply impossible to achieve using such frameworks. We then figured out that we can exactly achieve boundedness of the models simply by restricting the form of neural ODE to be linear quadratic, and then by adding some energy constraints over the linear and quadratic parts of the model. And how do we do this in practice? So starting from the first formulation of the neural embedding model, making it bounded, which also makes it generalized to any initial condition, even if given far from the observations, can be simply achieved by restricting the form of the neural ODE model to be linear quadratic, and by adding some energy constraints over the linear and the quadratic parts of the linear quadratic model. we then tried our bounded version of neural embedding model on the Lawrence 63 dynamical system. And when compared to the initial neural embedding formulations of unconstrained version, the constrained version actually can simulate Lawrence 63 dynamics, doesn't diverge after a finite amount of time, and more importantly, even if given an initial condition that is farther from the observations, the boundedness constraints make sure that we are getting into the spawned attractor by the observations and we stay there to infinity. We then tried this framework on a case study that involved sea level anomaly observations that are coming from the Western Mediterranean Operational Forecasting System, the WMOP, which is a realistic high resolution regional ocean model with a spatial resolution of an interpolated field of 0.05 and a temporal resolution of 1 day. And the considered case study area was located in the south of Mallorca. And in this case study area, we actually filtered the large scale kind of seasonal variability of the sea level anomaly. And we divided the data set into training and testing set, and we reduced the dimensionality of the considered case study using AOF decomposition. So what we did here is that we simulated two neural embedding simulations starting from slightly different initial conditions. And when compared to the true WMOP simulation, we can achieve a good short-term forecast. Our model doesn't diverge and keep simulating kind of realistic spatial temporal structures with respect to the true WMOP simulation up to infinity. And actually, regarding the two neural embedding simulation, even if they start from slightly different initial conditions, they diverge from each other after a finite amount of time, and they start kind of simulating their own version of the future. Okay, so the main kind of takeaway messages of this part is that we proposed a new kind of dynamical embedding approach for the forecasting simulation of partially offset systems. And from my point of view, sorry, what is most interesting about this framework is that the augmented space is built with variables that are here to minimize the forecast of the observations. They are here to explain the variability of the observations. So they are kind of intrinsically linked to what we do not observe. And also, the framework is bounded by construction, leading to potentially relevant long-term simulation of the dynamics, and I will talk about the potentially in the perspectives. So moving now into neural embedding with linear models and with some applications to spatiotemporal interpolation or data assimilation applications. So after this work, we started kind of investigating the link between the dimension of the embedding and the parameterization of the neural ODE model. We then figured out that actually linear parameterizations provide a theoretical link between our framework and the derivation of the stable modes of the Koopman operator, which is a linear operator. Now, we actually then thought that linear representations are extremely variable for data assimilation applications because they allow us to use extremely simple state-of-the-art kind of Bayesian filtering techniques such as the Kalman filter. And also the linear representation can also be provide a good short-term forecast of chaotic dynamics if those chaotic dynamics have some periodic or periodic and quasi-periodic modes, or more generally have some stable parts in their spectrum. So quickly, what this Koopman operator is about is simply, so assuming that we have some nonlinear dynamical system F that evolves the state X in time, the Koopman operator actually propagates in time observables of the state X linearly. And the issue now is the fact that this operator can be infinite dimensional. And this framework is actually quite old, and it was up until recently that people are trying to investigate kind of learning-based approaches and data-driven techniques in order to find a good finite dimensional approximation for this operator that can be useful for forecast simulation, data simulation. Okay, so quickly, a quick look into some, not all, some of the modern kind of state-of-the-art literature on the derivation of approximate Koopman representations. So assuming that we have the following state space model with a hidden state that we do not observe and with some observations, kind of the first kind of classical state-of-the-art techniques, what we call dynamic mode decomposition, simply computes the best linear fit that advances the observations in time. The extended dynamic mode decomposition, what it does in order to approximate this operator is simply by computing the best linear fit that advances observables of the observations in time. So there is this FP of X here, and it can be alone without the X, but this FP is simply a parametric family of nonlinear functions. For example, polynomial observables can be used in order to, for example, linearize nonlinear equilibrium points, and delay limiting observables are most of the time used with SVD representations, or in order to kind of linearize nonlinear oscillations and quasi-periodic signals. Now, there is a current trend in using neural networks and deep learning approaches in order to find some observables that can be propagated linearly in time. Now, the issue within all of these state-of-the-art techniques is the fact that they do not account for missing processes or use taken delay limiting. And another issue is the fact that augmented space, so the FP here or the neural network, actually depends on a predefined family of nonlinear functions. And for this predefined family of nonlinear functions, the suitable Koopman operator that linearized dynamics may be missing. So what we propose from here, it's extremely similar to the neural limiting model, is I'm extremely sorry for the busy slide, but it's extremely simple. You'll see. So assuming that we are provided with some measurements of some nonlinear dynamical system, what we do is that we project these measurements into a higher dimensional space that is concatenated to other unknown observables. And we assume that this higher dimensional space is governed by linear differential equation. We then optimize the parameters of the differential equation and the initial conditions of the observables to minimize the forecast of the observations. So we end up with a reconstruction of the observables and with the identification of a dynamical system that can be used to forecast linearly the observations. We actually tried this framework on several kind of nonlinear dynamical regimes, such as equilibrium points, nonlinear oscillations, chaotic dynamics, and stochastic dynamics. But I will mainly talk to you today about this case study of forecasting the large-scale kind of seasonal variability of sea level anomaly from WMAP. So here at extreme left, WMAP, the true WMAP simulation, in the middle, the projection from neo-geodesics. So this is the best forecast we can achieve. And here, the Koopman forecast. And what actually happens is that we are able to kind of predict the large scale kind of seasonal variability, but we lose on kind of the fast scale variability and the Algerian current because it's highly turbulent. And this is kind of expected because we are not expecting our model to kind of reflect the chaotic variability, because it's something that is not unstable. It's a part of the continuous spectrum of Koopman, and it cannot be modeled using our framework. Now, some talk about spatiotemporal interpolation issues that we did during this work. We considered as a case study spatiotemporal interpolation of sea level anomaly, which is observations that involve extremely high missing data rates, which leads in practice to an actual effective spatial resolution being relatively low. And within the both the satellite and physical oceanography communities, there is a huge emphasis in involving the high resolution kind of variability, which led them to either explore new sensing missions or to exploit learning-based approaches and data-driven approaches. So extremely quickly, spatiotemporal SLA interpolation problem can be defined as, given some irregularly sampled observations, how to find an inversion method that maps these observations into a regular spatiotemporal grid. And from a learning point of view, several techniques can be used. The first kind of category of techniques is what I call the plug-and-play schemes, in which we try to optimize a dynamical prior on some kind of already there reconstructed observations. We then plug this dynamical prior into kind of classical data assimilation schemes, such as the Kalman filter or an ensemble Kalman filter, in order to do reconstruction. Now, such schemes are extremely versatile, since they do not depend on the sampling of the observations. Now, the issue within sea level anomaly is the fact that we do know this sampling of the observations. It corresponds to the orbits of the satellites, and using it as an additional information can lead to better representing the high resolution scales. This leads us to the second category of methods, end-to-end learning schemes. From a deep learning point of view, it simply means, so this inversion method is can be seen as, for example, a deep neural network that takes spatiotemporal irregularly sampled, observations of sea level anomaly and map them into regular spatiotemporal grids. Now, this kind of techniques, they take full advantage of the observations and their sampling. They are, however, limited when considering generalization applications, or they are extremely hard to diagnose. So there's lots of issue in just using a neural network to do the job. So what we try to do is to take kind of ideas from both these two words and define a classical sequential filtering schemes of the Kalman filter in an end-to-end setting. So what we did is taken observations. We send those observations to a Kalman filter that have as a dynamical prior the Koopman model I presented earlier. So we get a reconstruction, we compare this reconstruction with some ground truth, and we get an error. We minimize this error with respect to the parameters of the dynamical system. Now, the issue within this formulation is the fact that this is why I call it preliminary work, because we are working on generalization of this work right now. But the issue within this formulation is that the Kalman filter actually don't have only the dynamical system as something that need to be parameterized, right? The observations and model error covariances are also need to be parameterized, and we cannot simply parameterize them using a minimization of the reconstruction cost, because this will only lead to a good ratio between the model observation error covariances, which gives a good reconstruction of the mean, but gives an extremely bad estimate of the uncertainty of the reconstruction. Now, in order to estimate the model error covariance matrices, we are now investigating how to include kind of maximum likelihood criterion into the learning in order to optimize these statistics. And we are kind of investigating the maximization of the innovation likelihood of the innovation, in order to kind of learn as well these covariance matrices. So the results I will show here are only based on the reconstruction cost. So I will only show you the mean. There is no uncertainty, but we are working on the uncertainty. So we are working on OSCC based case study. So based on the WMOP simulation. So we divide WMOP into training and testing sets, and we sampled we sampled observations from real satellite tracks from 4 altimeter configuration in 2014. And when we compare the proposed framework to classical optimal interpolation, we get an extremely good improvement. And when comparing to local analog data assimilation, we do slightly better in the reconstruction of the mean. There is no uncertainty in here. Now, this is a visual analysis of the reconstruction of February 19, 2015, so in the test set. And so the first line here is the ground truth gradient of the ground truth and the observations, optimal interpolation, analog data assimilation, the proposed framework, and the last line is just the gradients of the reconstructed field. And when compared to optimal interpolation, all of the data-driven frameworks do better simply because we know that OI smooths the finer scale structures. And when comparing our framework to the analog data assimilation, visually, we know that we are doing better simply because of the visual analysis of the gradients. Okay, this is the issue with the statistics that I was talking about earlier regarding how to generalize the proposed framework to optimize not only the dynamical prior, but also the model error covariance matrices. And it's through maximization of some likelihood. We are using the innovation likelihood, but we can also use the total likelihood or some other likelihood. Okay, so the main takeaway messages of this part is that we propose new algorithm for the identification of linear approximation of high dimensional and nonlinear dynamical systems. And those kind of linear representations are actually relevant for the forecasting of various dynamical regimes, including chaotic dynamics that have some stable signatures in their spectrum. Now, finally, the linearity of the model makes it suitable when considering spatiotemporal interpolation applications because simply it allows us to use extremely simple kind of state-of-the-art filtering techniques such as the Kalman filter. Now, moving to the conclusion, I actually hate writing conclusions because I do think that all of the work, for example, I presented here is just the start of getting towards the complexity of understanding the ocean or reconstruction fine scale variability of the ocean. But if I need to write a conclusion, I would say that this work shows just a little bit the potential of using data-driven approaches in deriving reduced order models for a subset of ocean variables. Now, in order to improve this work, directly the tools I presented here, there is several questions. For example, how to model the fast scales or how to explicitly include the influence of the fast scale through our proposed frameworks. There is the question of constraining chaos because when I showed you regarding the boundedness constraint, what we are doing is that we are constraining boundedness, but we are not guaranteed to have chaotic solutions. And how do we deal with this in practice? Is that we cross-validate, right? So every once in a while, we stop the training and we verify that, okay, our forecasting cost is good and the solution is chaotic, spectrums are good, perfect, it's a good model. And how to make it automatic means that we need to constrain chaos. And this is an extremely hard question to answer, actually, at least from a modeling point of view. There's also the question of how to model stiff phenomena and with all the repercussions on which integration scheme to use, because the integration schemes that are good for non-stiff phenomena are not necessarily the best to use. Even adaptive step size one are not necessarily the best to use when considering stiff differential equations. Now, when moving towards real observations, or how to model real observations. And I think that there is kind of three angles to take in order to kind of use real spatiotemporal ocean observations in deriving the models. The first one is using data-driven techniques. So pretty much what I presented during all this work with the extra concern of how to deal with irregularities in the data. Another solution is, another question is, utilizing kind of starting from already there kind of reduced order physical models and try to complement them with learning, with learning closure terms, missing physics, boundary conditions, with respect to the forecast of some observations. Now, some thoughts regarding artificial intelligence for ocean global circulation models. I think that AI techniques should be built online within ocean global circulation models in order to make them kind of interact with the physics of the ocean global circulation models. And in order to achieve such a thing, we need to write our ocean global circulation models in differentiable frameworks. And this thought actually arises lots of questions regarding, is it even possible to write an ocean global circulation model in differentiable framework? And if we do it, what is the cost of the backward pass? Is it even tractable? I mean, do we want to still stick with classical kind of discretization techniques, or go to neural solver because they can be more flexible, and lots of questions like this. Okay. Thank you very much. This is some bibliography, and I would be happy to answer some questions.
Thank you, Said, for the very nice talk. It is indeed very informative, including a lot of interesting things.
Thank you. I hope that I didn't explode the time, though.
No, it's fine. It's fine.
Oh, perfect.
So for people who have questions, you can either unmute yourself, or you can type your questions in the chat, and I will read your question for Said to answer. So meanwhile, maybe I want to start since I have some questions. So at some point at the first part of your presentation, you showed that the performance of your narrow and bending methods actually overperform the purely data-driven method like LSTM for predicting the Lorentz system.
Yes.
So I was wondering how about how about the training time then, since you will need to include this physics information in the loss function? Will that take much longer time to train the narrow and bending model?
The training, I mean, this is, I didn't do an analysis of the complexity of the training of the models, but as a naive question, I would say yes, because especially when considering high dimensional dynamical systems, this is just a 3-dimensional model. So at the end of the day, the differences between our framework and the LSTM is not it's not very big in terms of computational time. But when moving towards higher dimensional dynamical systems, I think that yes, the training time is a little bit larger, but it's still not that. It's not that much of an issue. Maybe the issue, if you have some issues, I will talk to you about issues. Maybe the issue is when including the boundedness constraints. So when including the boundedness constraints, we have this term here. So lambda1 mu t, the nonlinearity of mu, which is
makes the loss function more complex too.
Yeah, the loss function becomes more complex, and computing this term actually takes a little bit of time. So we are thinking now about how to reformulate in this constraint, how to put them, how to switch from soft constraint to hard constraints and stuff like that.
So actually, my second question is related. So I wonder if you have any like experiments or any insights to say if you can include this physics information in the, for example, the LSTM model to add these like physical constraints. Well, that in that case will lead the LSTM to somehow a similar performance to the narrow and bending methods. Do you think that would be possible?
I mean, in order to, the reason behind, the reason why adding these constraints was quite natural in our framework, simply because we are formulating the problem as learning of the differential equation. And then we found out that there is this guy, so Schlegel and Nowak, they just wrote a paper on how to make linear quadratic models bounded. And this can be directly put into our framework because we are working with differential equations. Now, in order to expose or do the same thing on recurrent neural networks, I'm not really sure because the form of the model is not the same, right? In recurrent neural network, we are not working on states of the system. We are working on an embedding, on the delay embedding, so it cannot be formulated as the time integration of the differential. Yes, it can be of delay differential equation maybe, but at least it's not straightforward.
Yes.
How to implement such constraints on recurrent neural network. Other constraints, I mean, we can do soft constraints, such as, for example, computing the Jacobian of the recurrent neural network and making it making it stable, but this is just promoting the stability. And all again, we do not want our models to be stable. So this is extremely hard question, actually, how to implement constraints on recurrent neural networks.
Yeah, probably there don't exist like this simple equivalence between these two. Thank you.
I think they should be studied at least.
Mm-hmm. Thanks. And I see there's a question from Cesar on the chat. So Cesar, do you want to ask your question, or you would like me to read your question? Okay, so probably I will read the question of Cesar. So Said, great talk and a very nice overview. So in your experience, do you think the Koopman approach on in the latent space can work better or worse than an autoencoder trend to go from T to T+1 in the full space? And what would you think will be the advantage and the disadvantage comparing these two methods?
Okay. Just to go back here. So the question is, just to make sure that I understood correctly, is does this Koopman method, how to situate it versus an autoencoder that reduces the dimensionality and moves one step ahead in time and then reduces re-augments the dimensionality in order to reconstruct the observations. And it's a little bit hard to answer because our framework will do better if there exists some stable part of the spectrum. So if the dynamics are not fully chaotic and there is some periodic and quasi-periodic modes, and we are interested in forecasting these periodics and quasi-periodic modes, so pretty much what I showed in this case study, where we want just to forecast large-scale variability, our model will do better because we are augmenting the observations with initial conditions that are optimized to minimize the forecast of the observation. So basically, when considering case studies such as EC surface temperature, the variability of the observations in an autonomous way, is not enough in order to do prediction, because simply when we project from the space of Z here to the space of X, there is missing information, and the space of X is therefore stochastic. So we need to send it into an embedding in order to make it predictable. So we are doing this, but in a linear way. So if this projection is not necessary, so if we are, for instance, observing directly states of Z and we want to just use an autoencoder in order to reduce the dimensionality and do forecast, then maybe the autoencoder will do much better than our model. But in the case where X is just partial observations of the system and of Z, and there is we are interested in forecasting the stable part of the spectrum, so periodic and quasi-periodic mode, then I think that our model will do better.
Okay, thank you, Said, for detailed explanation. So I just see there's another question from Jake in the chat. He would like to know if the code of your project can be available at GitHub.
Yes, actually, the code of the first part here, so before the boundedness constraint, are available on GitHub, and we will soon enough put the code of the bounded version on GitHub, because we did not publish yet the bounded version, actually.
Do you have the address of your GitHub?
Yeah, sure. I'm looking for it right now.
Okay, great. Thank you.
It's in GitHub Oceanics. It's a GitHub repository, and it contains lots of cool other projects. It's not only mine, but you can check. There is some 4D var stuff and stuff like that. Okay.
Okay. So in the meantime, we're actually running out of time, but I wonder if someone has a final quick question to Said.
No, actually, I had a few comments, especially regards to the dimensionality of the data set. But I'm sure we can have other opportunities to talk about that as we are running out of time now. And yeah, but anyway, I would like to say great talk, very nice overview. And yeah, so thank you, Sibo, for inviting you, and thank you for attending.
I mean, thank you for the invitation, and I would be extremely happy to actually talk with you on the issue of the dimension of such models, actually, because it's not as straightforward as we want it to be, actually.
So thank you again, Said, for giving this nice talk, and thank you everyone for attending this talk. So hopefully we'll meet later in person after the pandemic. So have a nice evening to everyone.
Thank you. Have a nice evening, and thank you again for the invitation. It was a great pleasure to present my work with you guys.
Thank you, and bye. Nice evening.
Bye. Thank you.